excited to be here and talk about my research on developing a machine learning model for monitoring ecosystem carbon dynamics. So to begin with, AI is no longer a distant concept. In different fields, we are seeing revolutions using AI. Forestry and environmental science is no exception. So in this work, we are trying to see if we can adapt machine learning models to track ecosystem change instead of the process-based models. Let me start with the motivation behind this work. Tracking carbon fluxes is really important to assess climate change. In general, carbon fluxes are assessed or predicted using process-based models. But the problem with process-based models is that these models are computationally expensive. So that's why we are trying to see if we can develop a machine learning model that can be used as an alternative to process-based model. So that's the motivation behind developing behind this work. So in this work, we developed a machine learning model using environmental variables as the inputs, and the output is key climate change indicators. In our case, I considered net primary productivity. In short, it's called NPP, and net ecosystem exchange. In short, it's called NEE. So there are three, I consider three meteorological variables and two output indicators to develop this model. So in this slide, you can see in the left side, you can see different process-based models such as Descent and Rothsey. So those are typically used for assessing climate change indicators. The process-based model uses equations to predict these environmental variables, and those are ecological theory-based. In contrast, different machine learning models, they learn from data. So the advantage is that it can learn the hidden patterns present in the data. So that is the advantage of machine learning model over process-based model, because we don't need any ecological experts to develop these models. So we can directly learn from the data using using our developed model. So here you can see the basic workflow of a machine learning model. So we need training data, then we pre-process that data, and we choose the suitable algorithm, and then we develop a learning algorithm to train the model. And finally, this trained model is used to generate the predicted results, and the results are used for our final outcome. So in this work, I started experimenting with different independent regression models, because my task is regression based. So I started with the simpler ones like the linear regression, Ridge regression, and then I tested different nonlinear models like multi-layer perceptron, k-nearest neighbor, support vector regression, and decision tree. Also, I experimented with the ensemble learning models. And I work with random forest here. So the basic principle of ensemble learning is that in ensemble learning, different base learners are integrated using a meta learner, and the final prediction is performed using the meta learner. So it works based on the principle of wisdom of crowds, because it's based on the principle that when we combine the verdict of multiple people, then it's generally better than a single people's verdict. And why these models works? Because a single model might not be able to capture the high variance or high bias present in the data. But when we combine different models and perform the prediction, then in general, it gives better performance by tracking the hidden patterns and tracking high variance or high bias in the data. Also, we tested a very recent transformer-based foundation model for this task, and these models are pre-trained on vast amounts of synthetic data. So we fine-tuned this model for our own task. So now for our task, random forest model performed the best. So I give you a brief overview how random forest model works. So in random forest, subset of samples are created using the bootstrapping technique, and then these subsets of samples are fed through the different decision trees. And finally, the results of these decision trees are aggregated using majority voting in case of classification, or averaging in case of regression. So this is how the random forest models performs its prediction. Then we also tested the foundation model TAP-PFN, and this model performed the best for when we decrease the size of our data set. And in general, these foundation models works best with limited data availability. So that's why we tested and fine-tuned our model to check the robustness of the proposed machine learning model. So TAP-PFN is a transformer-based model. The main architecture is transformer-based, and it is trained using synthetic data, and it performs the final prediction using in-context learning, or ICL technology. Also, the model is prior fitted and uses a Bayesian prior fitted modeling techniques. Yeah, so this is our proposed framework. So in this work, we investigated a multitask approach for predicting both the key indicators of climate change. Those are net primary productivity and net ecosystem exchange. In this model, the parameters are shared for this task, and the joint prediction is performed for both of these variables. And we found out that when we perform the joint prediction, it performs better compared to the single prediction. Compared to the single prediction. So here you can see, here I have been listed the input and output variables for the model. So I have considered soil temperature, air temperature, and precipitation. And for my output indicators are net primary productivity and net ecosystem exchange. In this figure here I have you can see the cross correlation matrix, and you can observe that there is a high correlation factor between the maximum and minimum temperature and the average temperature. It's around 0.99. So that's why we only consider the average temperature instead of the max and mean temperature. So it decreases the dimensionality of the problem and also handles the multicollinearity problem. Also, you can observe another interesting pattern. It's that you can see a high similarity between the two primary key indicators, NPP and NEE. It's around 0.93, which also supports the design of a multitask model for solving this task. As my task is regression based, so I have considered three key indicators. Those are mean absolute error, MAE, root mean square error, RMSE, and coefficient of determination, R2. So the first two variables are related to error metrics. This indicates how the predicted variables are performing compared to the original values. And high R2 with a lower MAE and RMSE indicates better performing model. So here I have enlisted the model performance metrics for NPP prediction, and you can see that the multitask random forest model is performing pretty well with 0.68 R2 compared to the other regressors. And you can also observe that linear regression and Bayesian regression is not performing well for this task. It means that the data has the data has nonlinear patterns, which has been detected using the multitask random forest model. And also for the NE prediction, in the table, you can see that the performance for our developed multitask random forest model is around 0.67. And yeah, here you also see the similar pattern. Linear regression and Bayes regression is not performing well for this task. And here you can observe the scatter plot for the NPP, comparing the observed and predicted values, and you in the right figure you can observe the yearly prediction. So for my training data, I have considered 1990 to 2024, and I have performed a futuristic constructed a futuristic prediction data set from 2025 to 2050. And here you can also see the results from NE prediction. You can, in the left side, you can see the scatter plot, and in the right side, you can see the yearly prediction. And also I have performed shape analysis to interpret the results of the machine learning model. In both of the figures, you can see that soil temperature is a main key factor among the input variables for both NPP and NE prediction, followed by average temperature, time, and precipitation. And in the shape analysis, you can observe that you can also observe that soil temperature is the main key factor with the highest spread between -2 to +6. So this variable is playing a key factor when we are performing prediction for NPP and NE. And also I have varied the, I have repeated the experiment for varying different treatments such as soil warming and nitrogen addition. And in both of the cases, I found out the machine learning, developed machine learning model is able to capture the distribution with a very good accuracy. And for nitrogen addition, it's quite higher. It's around, the R2 score is around 0.8. In both of the cases. Which shows that the model is generalizable for different treatments, which is a very good which is a very essential characteristic when we are justifying a machine learning model's performance. And to check the robustness of our proposed model, I have decreased the training data set size. So in this case, I have considered the training data from 1990 to 2000. And I found out that although the performance of multitask random forest model has decreased sharply, but in this case, TAP-PFN is performing quite the same with an R2 of 0.65 for NPP and an R2 of 0.63 for NEE. So yeah, in future, I'd like to explore transfer learning for this task because one model trained for one biome may not be transferable to another biome. And in general, we need to perform transfer learning to make the model more generalizable. Then we can also think of incorporating or developing a physics-constrained, physics-informed machine learning model where we can incorporate the ecological constraints directly into the machine learning model. And to think and to consider about the robustness, we can assess the uncertainty quantification in terms of when we are making predictions, and also we can also consider the uncertainty of the data. So yeah, that's all I had for today, and thanks for listening and attending the session, and I'd be happy to take any questions.
Thank you very much, Dr. Firdaus. Perfect timing. All right, Dr. Spath, if you want to handle questions in the chat.
Thank you, Dr. Gray. Hope all is well. So there was 2 questions so far, and y'all can continue to ask questions as I'm given these other ones. So what was your motivation behind applying AI and machine learning to a climate change application?
Uh, so can you please repeat the question?
Okay.
Sorry.
What was your motivation behind applying AI and machine learning to a climate change application?
Okay, yeah. Actually, I gave a brief overview on this at the beginning of my slide, but I would like to elaborate on this more. Um, so, um, in general, uh, when we develop a machine learning model, we try to optimize some process. So in this case, to track climate change, there are already different process-based models. So to track climate change, these models are really time costly. I mean, it takes 24-hour or something like that to generate predictions on key climate change indicators. But when we are training a machine learning model and we are performing predictions with these models, this can be scaled down to smaller than 1 second, or I mean, we can perform the prediction very fast. So for real-time prediction, we need machine learning model instead of the process-based model. So that was the main motivation for developing a machine learning alternative for process-based model.
Awesome. Um, the other question is, speaking of performance, could you elaborate on how the AI machine learning based model compares to a traditional process based model in terms of prediction speed?
Uh, so in terms of prediction speed, when we compare these two models, we cannot perform prediction in real time using the process-based model. Also, we need domain knowledge when we are training the process-based model. But when we are working with machine learning model, we really don't need the domain knowledge. So we can feed the data to the model and then pre-process the data, and we can get the results within seconds. In terms of, I mean, time complexity, it decreases the time complexity a lot. And in terms of prediction performance also, we get very good accuracy with machine learning models compared to the process-based models. Also, another problem with process-based model is that these process-based models are very generic to one data set or one biome. When we are developing a machine learning model, there is a chance for model generalization. One model trained for one data set, we can generalize with different techniques like transfer learning or few shot learning. So these are the advantages of a machine learning model.
Amazing. There was one that asked you what are the implications of your great research. I guess how can we benefit from the research in real life, basically.
Yeah. Yeah, in real time or real life monitoring or real time prediction, process-based model would not be a right choice. So in that case, machine learning model would be the right choice when we are performing real time prediction. So when we are talking about deploying the system to production and using it in real time, so we definitely need the machine learning alternative instead of the process-based model.
Awesome. And I think our final question, unless someone pops up another one, what was your biggest challenge when applying AI models in climate research? And what recommendations would you have for future researchers doing the similar studies?
Okay, so my biggest challenge was getting the data set. So I generated the data set using a process-based model using Descent. So getting these kinds of, I mean, real-time data is really costly. That is the biggest challenge, data availability. Also, data quality is another challenge. When we are feeding this data, we need to ensure that the data is of high quality and it's matching the distribution of real time. I would say these are the biggest challenges. And also, I was thinking of integrating data from different sources for this specific task, but it gets quite harder when you think of integrating or fusing data from different sources, because different data sources have different formats, and sometimes the input variables do not match. So in this case, I mean, you need to figure out, or you need to think of the ways how to fuse this data. So these are the challenges that I faced.
Yeah, collecting data is very hard, especially in quantitative studies. Um, and what recommendations, I guess, could you touch on recommendations for future researchers
Uh,
to go
so my
beyond, yeah, to go beyond your study? Future
okay,
recommendations.
okay, yeah, sure. So my recommendation would be to keep yourself updated and try to learn new things, and so that you can keep up with the new innovations, because you always have to push yourself and you always have to push your boundaries. And these days, I mean, new models, new research is releasing every day, and actually every second, I would say. So yeah, you need to always keep yourself motivated and updated, and yeah, with the new trend.
It's hard to stay motivated, isn't it? It's so much information getting bombarded all the time, right?
Yeah.
And, and then I think another question popped in: how would you select those data as soon as possible? With so there's so many sources and data, how would you select those data as soon as possible? Um,
So yeah, one way I use selecting the data is I perform literature review. So I get a understanding, I mean, what the other researchers are doing in this field, and what are the important data sets or criteria they are looking for when going for a data set. Then I apply my own knowledge or apply my own ideas. So I think this is the best way you can think of coming up with a solution.
Perfect. That was all the questions that we could take for tonight. Dr. Gray, if you want to take over.
Absolutely. Thank you so much, Dr. Firdaus, for a wonderful presentation and for taking the time to answer the questions from the group.